Hello everyone. We are going to see the fourth unit. That is water. My name is Dr. Ganesh Agawne. To those who are interested in studying water, they can watch this entire lecture series and understand various concepts of water, various problems associated with water, various properties of water, various quality parameters of waters, and uh, why we have to study water itself. First and foremost, a question in everyone's minds may arise that though everyone knows water, life was originated from water itself. We call life is equivalent to water, or water is equivalent to life. Then, particularly for engineering students, why do you think this introduced in our curriculum, and why we have to study water, right? So, first of all, we have to understand the background and motivation behind implementing or introducing this unit for engineering students. So why there is a need to study water, right? Though everyone knows it's essential for most of the living systems, most of the biological processes, reactions, and then there wouldn't be life if there is no water. And the life itself on the planet Earth is just because there is a water, right? But that's a side apart. We have to say something different. For engineering students, for engineering applications, we consider water as an industrial solvent. When it comes to industrial solvent, that means we may use, or we will use, or we are using water for various industrial applications, engineering applications. Now forget about agriculture applications, pharmaceutical applications. It needs water for 90% of the processes, but especially for engineering applications like conversion of electricity, that is hydroelectricity, conversion of electricity from by using coal. So coal will be basically used just to boil water, and everyone knows there are so many power plants in Maharashtra and in India also. So as we know, 70% electricity, or 65 to 70% electricity comes from these power stations, where they have large boilers. Now the boiler's function is to create a huge amount of steam. The steam will be used to rotate turbines, and turbines are connected to the generators. So the generator, and finally generators will generate the electricity. Now the boiler will be boiled with the help of coal or different type of energy sources. But the basic fundamental thing is water. Now consider this water is impure. The water which is there in the boiler, large boiler, which is creating a huge amount of steam to create the electricity. Now consider this water is a impure water, hard water, has biological impurities, organic, inorganic salts present in the water. What will happen? What do you think? Any guesses? And that is why we have to study water in detail. Structure of water. Now, this is the structure of water, which shows uh, there are two non-bonding electron pairs, which is generally caused because of the lone pair of electrons on two lone pair of electrons on oxygen, and bonding electron pair causes another triangle, or 104.4 angstrom unit angle, because of two hydrogens. Now, if we consider the entire structures, considering two hydrogen atoms and two lone pair of electrons, which makes this dumbbell shape orbit, and that gives tetragonal electron pair geometry, and that makes uh, or that gives tetragonal structure to the water. The next slide will show what are the various sources of water. That was just an earlier slide, which just or showed what are the various properties or basic, just one property among the so many properties, that is just the structure of water. So many other properties are there, like having high dielectric constant, having universal solvent nature. It has no color, it has no taste. The conductivity, electrical conductivity is less when the water is highly pure. It has no color. Uh, if some impurities are there, then only it will cause, or it will have some kind of odor, color, change in taste, conductivity will be increased, turbidity. Now, pure water, remember, will have very less turbidity or no turbidity at all. Now, turbidity is generally caused because of the dissolved solids, remember. You might have seen the water during monsoon. Can you just imagine, or can you just remember uh, the water which you have seen during monsoon and the same water you have seen during summer or winter? Can you see, or can you imagine any kind of differences between these two waters? During monsoon, we can see the water is little bit murky, right? Murky or turbid. That is because of dissolved solids. That means there is a constant rain at some point, and the water flows from one end to another end. When it travels from one end to another end, having high dielectric constant and universal solvent nature, it will dissolve those organic impurities or salts which are coming in contact with water, and ultimately those impurities will come in water, and that will be present in the form of dissolved solids, and that gives the water a turbid nature. Okay, these are the various another basic fundamental properties of water. Now these are the next slide shows various sources of water which we can see, that is rainwater, that is underground water, there is surface water, springs, tutorials, and then there is a well as well. What are the various impurities present in water? Next slide. Let's see. See, basically it has impurities like suspended and colloidal particles. That means organic and inorganic salts, dissolved salts or compounds. Then microbiological impurities or biological impurities. Sometimes we may not say it's micro size because uh, generally, some impurities will have a size larger than micrometers, and sometimes some microbiological impurities will have sizes or size less than micrometers. So biological impurities, let's call it biological impurities, and then dissolved solids are there, and this collectively say, or collectively we call, these are the various impurities. Now, what happens when these impurities are there in the water? Let's see. Next slide shows water quality parameters. Now, basically, there are three parameters: physical examination or physical parameters, then chemical parameters, and then biological parameters or biological impurities. Parameters or impurities we can call uh, alternatively. Okay, so physical properties or physical parameters, physical impurities. If the water is highly pure, it will have no color. It will be colorless. If the water is pure, then the water will have no odor and taste. If the water is pure, it will have less conductivity and no turbidity at all. If the water is impure, and then the turbidity will increase, conductivity will increase, as we know, and odor, it will have some odor because of sulfates, nitrates, chlorides. Color will be different because of some transition compounds or transition metal salts. Chemical impurities or parameters. So many parameters, chemical parameters are there. Among those so many parameters, we are only going to study in our syllabus, that is hardness, chlorides, and alkalinity. That means why we have to study hardness. That means there must be something like soft when we say hard, right? So basically water is divided into two types, that is hard water and soft water. The water which does not form foam after the addition of detergent or soap is known as hard water. So generally it forms a scum or precipitates. Okay, so basically it should not form precipitate when the detergent is mixed or added. Chlorides generally cause, or incorporate or make the water hard. Also, chlorides will cause corrosion. Alkalinity, higher the alkalinity, that means the water is more alkaline. Okay, and it is also not good because if it has a highly alkaline nature, what happens? It forms hydroxide compounds very easily and precipitates can be formed. So it should have relatively neutral pH, and therefore we are also going to study the next third property, that is alkalinity. And then in microbiological or biological impurities, we are going to study biochemical oxygen demand. There are biological oxygen demand and chemical oxygen demand. It's BOD and COD. So the physical examination, physically we can just see if the water has different color, then we can say it has some impurity. So basically it is a colorless. So color will be caused because of some dissolved compounds, dissolved solids, colloidal impurities, industrial waste. Green or orange color, generally if the water has a green or orange color, generally it is caused because of phytoplankton, and this can be tested visually or spectroscopic techniques. Units are there, that's like Hazen units for colors. Now, so many other techniques are also there to test the various properties of water, but you see, we are only going to study or see simple properties of different colors, different impurities, sorry. Then next is odor and test. So if the water has some odor, as I said earlier, the water has no taste and water has no odor if the water is pure, right? Now, if it has some odor and taste, some kind of test, metallic test, organic or sour test, sweet test, any kind of test, then it will have some impurities like volatile compounds, medicinal compounds or medicinal organic compounds like phenolic compounds. Fishy test or odor is that will be that will be caused because of algae, and chemical tests generally because of chlorides or chlorine and sulfates. This can be removed by chlorination or precipitation. Simple precipitation or gravitation, as we know. Uh, Conductivity, next impurity or next parameter is conductivity. So the measure of concentration of mineral. That means highly impure water or the water which has more inorganic salts will have more conductivity. Everyone remembers Three Idiot scenes, right? So that's a very good example of a good conductor. Water is a good conductor of electricity. So everyone knows there are salts, and because of it, it becomes more conductor. So pure water will have less conductivity, while impure water, when there are inorganic salts, phenolic compounds, aromatic compounds, chlorides, will increase the conductivity of the water. So higher the conductivity, highly polluted, or higher the impurities, or very high impurities. This can be tested by electrolysis experiment as well as simple microscopic examinations or spectroscopic examinations can be done in order to check this conductivity impurity parameter. Next, the physical examination or impurity parameter, that is turbidity. As I said earlier, during monsoon, we can see the water is more turbid because of dissolved suspended solids. Now, measure of now turbidity, actually it is the measure of light absorbing properties of water sample. So if the water absorbs most of the light, we can say the water is highly turbid, right? So it is measured with, with respect to silica scale. Okay, so we can see there are four glasses here: one, glass number two, or beaker number two, and beaker number three, and beaker number four. Right? This beaker shows highly turbid water, while this beaker shows more clear water. So the low turbidity and the arrow shows low turbidity, high turbidity. So as we go from left to right, turbidity goes on increasing. The water is collected, or we can say this is turbid water, and then this is a color water. Simple, suspended, dissolved, colloidal impurities. Can we allow this water, if you allow to settle down with a simple gravitation technique, dissolved solid compounds can be filtered or can be simply removed. Okay, so how to remove? Can be removed by filtration and sedimentation. This is generally caused because of suspended particles. This is the last physical parameters. Then biological oxygen demand and chemical oxygen demand. Let's see, microbiological investigation, or BOD and COD. Now remember, highly pure water will have very less BOD. Very simple logic to remember. And highly impure or more polluted water will have very high BOD. Now, this is a simple explanation, a very simple explanation shows, or you can see, pure water will have very less BOD, impure water will have very high BOD. That means the aquatic life, marine life, or microbacteria which are present in water will need more oxygen in order to convert this organic or convert the organic matter into the stable products. It will need more oxygen, right? And therefore, we can say the water has high BOD, biological oxygen demand. So, microbacteria will demand so much in order to convert the organic matter into stable products. And it is quite obvious, when the water is highly impure, microbacteria will need more oxygen. Because of impure water, there is very less oxygen. So this will need more oxygen, and the OD value will be increased. Simple explanation. Similarly, in case of chemical oxygen demand, this is the measure of oxygen equivalent of organic impurities present in water, which are susceptible to oxidation by strong oxidizing agents like potassium chromate. Remember, so BOD general definition is amount. It is the amount of oxygen required by bacteria while stabilizing the composable or decomposable organic matter. BOD. What are the various values? Simple values you just have to remember. You don't need to go in so detail. No, the notes will have more explanations. Just to read it, but remember just to value some values of BOD. That is, potable water will have, as I said earlier, you see, potable water will have very less BOD. It's 1 to 3 milligram per liter. Remarks reasonable. It's okay, acceptable. We can drink. River water, tolerable, we can still drink. No problem. Or organic matter can be converted into stable products in the potable water, in river water. But for microbacteria, it will be very difficult to convert this organic matter into the stable products where there is the water source is like sewage, or the water has direct, what do we say? The water has impurities directly coming from the industrial wastes. So the BOD will be very high, nearly in the range of thousands milligram per liter. So it will demand so much oxygen in order to convert this decomposable matter into stable products. So remarks shows industrial wastewater is highly bad or highly impure, extremely bad. Next slide shows hardness of water. Very simple experiment which everyone has done in the laboratory, right? Everyone has done. I hope. I hope everyone has done. So we took sodium EDTA, right? Sorry, EDTA, ethylene diamine tetraacetic acid, and then metallic, bimetallic, oh sorry, uh, calcium, or we what do we say? Uh, we complexed Ca++, that is bivalent rare earth metals like magnesium and calcium were complexed by EDTA with the help of EDTA. So we complexed using EDTA, and hardness was calculated in terms of parts per million, as, as everyone knows. So generally remember, hardness of water, we will say the water is hard if the hardness of water is higher than 100. Till 100 it is soft, though it is given 50 to 100 moderate level, but it's still soft, not a problem. We can digest, we can drink, not a problem. We can use for industrial application, not a problem. But if the hardness is higher than 100, then the water has to be treated before it is used for industrial applications or biological, like for deep drinking purposes. It has to be treated. So these are the various ranges. From 0 to 50 it is soft, 50 to 100 it is moderately hard, 100 to 300 it's hard, and the last one is 500 to 1000 ppm. It is extremely hard, cannot be used for any kind of applications, whether it's agricultural applications or purposes, pharmaceutical purposes, industrial purposes, or drinking purposes. So this is the very important property which is determine hardness of the water. Did you understand? I hope everyone has understood. So we just simply complexed with the help of sodium stearate, right? Uh, no, sorry. This is just sodium stearate, that is soap, plus calcium chloride. That means if some hardness causing compounds are there, that is calcium and chlorine, and then instead of forming foam, it will form scum. It's calcium stearate in the form of calcium stearate, right? And the water will be called as hard water. There are basically two types of hardnesses, as everyone knows. We have calculated as well: temporary hardness and permanent hardness. Temporary hardness is caused by, as everyone knows, carbonates, sorry, or uh, rare earths like calcium, magnesium, and permanent hardness is generally caused by chlorides, sulfates, and nitrates. Right? This collectively becomes total hardness. Temporary hardness can be simply removed by boiling water at 100 degrees Celsius for more than 10 minutes. Now you see, the water has to be boiled more than 10 to 15 minutes. If we are simply boiling for 1 or 2 minutes and then trying to remove the temporary hardness, it's a little difficult. So it's better if you want to make water, especially during monsoon, you want to drink soft water recommended by the doctors. It's better you boil it for minimum 10 minutes. Okay. Temporary hardness caused by carbonates, right? Magnesium carbonate or calcium carbonate or calcium bicarbonate. And these are the various reactions which occur. Magnesium bicarbonate converts into magnesium carbonate and then magnesium hydroxide and CO2. This arrow should be above, not downward arrow. Okay, that was a mistake. So if you see what happens with a simple impurity like magnesium bicarbonate, If there is no such impurity, what will happen? If the water is heated, delta shows for heating at 100 degrees Celsius. If there is no any kind of impurity, the entire amount of H2O will be converted into steam, and the water can be used for steam generations of steam. Now suppose there are bicarbonates like magnesium and calcium. This will convert this bicarbonates into carbonates, and finally, if the same water is boiled for a longer time, then what happens? It will convert this into hydroxides with the evaluation of seawater. And hydroxides are generally not good. It will form precipitate, and ultimately it will start corrosion of the boiler, right? Same reaction can be seen for calcium bicarbonates. Okay, permanent hardness. Next, we have not given any reactions here, but see, then generally it is caused by chlorides, phosphates, sulfates, hydroxide, nitrates of calcium and magnesium. This can be removed by ion exchange and RO, that's reverse osmosis, which we are going to study in detail later on. What are the disadvantages of using hard water? Now, as I said earlier, using hard water is not good. So it forms scum mixed with soap and calcification on tap of the surfaces, corrosion of the metal surfaces, corrosion of the boiler, and so many blockage of the pipes which supply the water to the urban population, right? So many other disadvantages will cause just because of the hard water. So how the hardness can be determined? Disodium EDTA salt can be used in order to determine the hardness of the water. A simple disodium salt can be used in order to determine the hardness. Okay. Now let's see. I hope everyone knows EDTA structure. It is a very simple structure. Okay. It's simply complex. It forms six coordinate bonds with the central metal cation, and complexes the calcium or magnesium metal. Okay, and that which can be removed later on. Now, initially, it is just like complexing and determining the amount of hardness. The removal of hardness can be done by using EDTA, that is disodium salt of EDTA, or some other processes like reverse osmosis or ion exchange techniques can be used. Now, actually, what is the experimental method? How this can be done? We take 0.1 molar EDTA solution in the burette. We take 10 ml water sample in conical flask and add 3 ml buffer solution, which has a pH 10, in order to maintain the pH of the conical flask solution or water sample. And then we titrate it against EDTA after the addition of EBT indicator. Now, initially, after the addition of iriochrome black tea indicator, the color change will be from colorless to wine red. When you are actually titrating against this wine red solution, that is water sample, with EDTA, your final endpoint will be wine red to blue. So blue is the original color of the iriochrome black tea indicator. So we are actually obtaining indicator as it is in the form of EBT. So EBT comes in this picture just to make unstable compound, that is calcium plus EBT. When you add 2 drops of EBT indicator, the moment you add 2 drops of EBT indicator into the conical flask solution, it forms wine red unstable compound. This compound can be broken or can be converted into calcium EDTA, and we can obtain or we can remove EBT as it is, which has a blue color. So that's your final endpoint. The observation table shows initial readings and then final and then difference. You take CVR constant burette reading, that means at least 2 readings should be same minimum two readings, first or second, first and third, or first or second. If you get two same readings, you don't need to go for the third one. You get CBR, use this for the calculations. Okay. Numericals we will see later on in detail. The numerical formula is very simple. Everyone has to remember this formula, which I have taught in the laboratory as well, which is very useful formula. That is 1000 ml 1 molar or 1000 ml of 1 molar EDTA is equivalent to, this is not equal symbol, actually it should be equivalent, remember, is equivalent to 100 grams of calcium carbonate. That means in order to complex 100 gram or 100 grams of calcium carbonate, we need 1000 ml EDTA, which has molarity 1 mole. With the help of this simple equivalence relation, we can calculate the amount of hardness. That is, hardness is equals to CBR, whatever your reading is, constant Beirut reading, multiplied by molarity of EDTA, then the amount of equivalent amount of calcium carbonate, that is molecular weight of calcium carbonate, divided by 1000, that is the amount of EDTA, right, is equals to, this will give the hardness value Y, okay, grams of calcium carbonate equivalent for 10 ml. That has to be converted into, we have to convert this value into parts per million. How to convert? Multiply this Y value into 10 raised to 5, that will give you, whatever the value is, that will give you the value in parts per million of, for hardness, sorry. So the total hardness will be in parts per million, okay. This is the simple reaction process which occurs during estimation of hardness experiment. Okay, so there is a Ca++ ion or Mg++, that is M plus 2 plus EBT forms at pH 10 forms unstable winded compound, is MEBT. Then MEBT compound will be broken when you titrate this MEBT complex with EDTA, and MEDTA will be formed. A simple reaction, and the final endpoint will be from winded, from this to final glue. Okay. How to remove temporary hardness? Temporary hardness can be removed by simply boiling the water for 15 minutes. So, removal of temporary hardness we can remove. You see, very simple technique. Take 500 ml water sample in a 500 ml beaker or little larger beaker, and keep the beaker on hot plate and boil the water for 15 minutes. Remove beaker from the hot plate and cool the contents. Filter the boiled sample using funnel and filter paper to another beaker, and discard the filter paper. The filtrate is only permanent hardness producing salt. Okay. So the filtrate above or on the filter paper, this will have, the solution water which is filtered, this will have now only permanent hardness. It's caused by sulfate, nitrates, and chlorides. It's generally removed, which is generally or little difficult to remove by simple boiling. Got it? How to remove, how to determine permanent hardness, which we have seen earlier. It's a very same process. There's nothing different. Okay. And then finally, how to calculate temporary hardness, permanent hardness, and total hardness. So temporary hardness is equals to, remember, everyone knows this is a very simple process. I just have to quickly remind or quickly revise. That is total hardness minus permanent hardness is equals to temporary hardness. Now the next slide, or in the next lecture,